So previously we had talked about the electric field and the force. We're gonna add a new quantity, the electric flux density, which is commonly denoted by the capital letter D. So this is called the electric flux density. And the way I like to view this, this flux density is just simply arrow density. Let's start with a point charge example where you have a point charge Q sitting, let's say, at the origin. The electric field will radiate outwards. And in this chapter, we'll also talk about Gauss's law. One of the things about one of the basic concept of Gauss's law stated in plain English is that if you add up all of these electric field arrows, so the total electric field arrows, all added together, is going to be equal to the charge. So if you add up all of these arrows, the total number of arrows is going to be equal to Q. So we can then use that to calculate the electric flux density. So let's just draw a sphere of radius r. The electric flux density will be the total number of arrows, which is Q, divided by the surface area of this sphere, which is going to be 4 pi r squared, right? And we can actually also point out that since these all radiate from the origin, if the point charge is at the origin, it will also be in the r direction. So this is the formula for the electric flux density of a point charge, and I'm just using that to also build some intuition and make an introduction for Gauss's law. So electric flux density is basically the number of arrows per unit area, conceptually. So arrows per unit area, and we did that for a point charge by just saying, by observing, due to Gauss's law, which we'll get to later in more rigorous detail, the total number of arrows is going to be equal to Q. So then the electric flux density is Q divided by the surface area of a sphere, 4 pi r squared r hat, right? And so you can see that the density is going to be inversely proportional to r squared. Just like if this was a light bulb, you'd expect the amount of illumination per unit area to decrease by inversely to 1 over r squared as you get further and further away from the light source. So this is kind of a similar thing. Now compare this to the electric field equation for a point charge. The electric field equation for a point charge was Coulomb's law, except we just take out the observer charge. So you have Q over 4 pi epsilon r squared in the r hat direction. By comparing these two, you can also see that the electric flux density is going to be equal to the electric field times a factor of epsilon. And in the case of a vacuum, epsilon is going to be equal to epsilon naught, which is going to be equal to that quantity that I defined earlier. But this changes with different materials. So when it's not necessarily vacuum, if we're generalizing it, I'm just going to call it epsilon. If it says epsilon naught, then that's going to be in the case of a vacuum. So in many cases, epsilon naught is epsilon naught is the minimum possible value. In many cases, it's some factor larger than that, which we'll just use epsilon r to describe. So epsilon is going to be equal to the relative permittivity, epsilon r, times that of a vacuum. But basically, the main thing I wanted to drive across is that if you compare the point charge equations, you can see that the electric flux density is related to the electric field through this epsilon term. So one thing to note by looking at this expression is that D is material independent. So it's independent of the material because there's no epsilon in the description. The number of the density of arrows per area is the density of arrows. And so that can be quite handy if you're going from one material to another. Since the fact that this electric flux density doesn't change between different materials, you can use that to as a way to set up your boundary conditions and see what the E field is when you're going from one material to the next. Another concept that I'd like to get across is let's go back to the fact that the force that you feel when you're given an E field is the E field times the charge that of the observer, right? So you put in this extra charge, the force that that charge feels is that charge times the E field. So let's just stick this expression in. It's going to be equal to 2D divided by epsilon. So one way to view this epsilon is saying for a fixed density of arrows going through, how does that translate to actually the force that I would feel if I stuck a unit charge in there, or the force that a unit charge would feel if it was stuck in there. And that is material dependent. So for a vacuum, you might feel a certain amount of force, but if you're in a different material, epsilon is going to get larger. Epsilon can only be larger than epsilon naught. Epsilon naught is the lowest possible value. So if you're in a non-vacuum material, what ends up happening is that for the same arrow density, you feel less force than you would in a vacuum. And that scaling factor is described by this epsilon. So again, I just wanted to introduce the electric flux density, which is, in plain English, it's the density of arrows per unit area. Arrows being electric field arrows in the case of electric flux density. And if you compare the two equations, they relate to the electric field through this factor of epsilon. And one way to view this epsilon is it kind of tells you how much force a unit charge feels in a particular medium when compared to if the medium was a vacuum.